Hi everybody, today we're going to look at a skidding bowling ball problem. If you ever go bowling and you put a lot of spin on the ball, this is what it should look like. Right, the motion's actually really complicated. Right, you could see the ball kind of spin really fast, and then eventually once it gets closer to the pins, eventually it just starts to roll. So actually that motion can be broken down into two segments. And the problem today is to kind of look at that in a little bit simpler than what real bowling is, because then you have all the side spin. But we're going to look at a problem that's analogous to this, but we're going to simplify it to make it easier to do some of the algebra and some of the physics. All right, so this is what the setup looks like. I have my bowler over here who's going to throw the ball at some initial velocity. Okay, I'm going to call that V0. So let's write that down. Initial velocity. And this is really the initial velocity of the center of mass, right? So it's really the center of mass here that's moving at some velocity V0. Now, when I'm going to throw the ball, I'm going to actually assume that there is no angular velocity. I'm not going to put any spin on the ball initially, right? So when it first leaves my hand, I'm going to assume that this angular velocity, and again, it's the initial angular velocity, is going to be 0 radians per second. All right, so I want to analyze the motion of this ball. What's going to happen here when it kind of slides down? In the first motion, it's really some sliding that's going on as it's sliding down the lane. So this is the sliding area, we're going to call it. And then after that, after a little bit of time and after it's covered a certain amount of distance, what we're going to have over here is before it hits the pin, this is when it actually just starts to roll and there's no more sliding happening. So we're going to try to set this problem up, look at the forces acting on the bowling ball, and analyze both of these sections. My goal at the end is to calculate how far this distance is and how much time does the actual bowling ball slide. So where is this point where it converts from sliding to rolling? So let's have a look at how we set this problem up. So here's my problem again. Let's now look at all the forces acting on this bowling ball. Here, I'm going to isolate the bowling ball down here. So the first thing is if I just plot the center of mass here, we have a weight, right? This bowling ball here has a weight. I'm going to call that W, and the magnitude of this force is simply mass times gravity. That's pretty straightforward. The next one we're going to have is a normal force, right? This bowling ball is actually in contact with the lane. That force here acts right here at the bottom, and that force is again going to act straight up. I'm going to call that N, and this is my normal force. Now there is another force acting on this bowling ball, right? And the other force here is an important force for bowling. It's actually a friction force, right? Although they may kind of wax the lanes and all of this stuff, the bowling ball is pretty smooth. There is still a little bit of friction acting on this bowling ball. And the force of friction here is going to act opposite of the motion, so it should be pointing to the left direction here. So these are the three forces that are acting on the bowling ball. And again, I don't have a force from my hand because I'm examining the motion once the bowling ball has left my hand. So this is it. So one thing that is important about this problem, and if you've looked at a little bit of rotation, you've probably seen this formula, right? That the velocity of the center of mass is equal to the radius times the angular velocity. However, one really important property of this equation is that this equation here only applies if it's rolling. So let me write that down. This is so important to understand. Only applies during roll, during pure roll. It doesn't apply when there's any skidding or sliding going on. So only applies during roll. So for this particular problem, I could not apply this equation here during the first segment, during the sliding portion. And clearly we know that because look I've given the ball some initial velocity over here. This could be 5 meters per second, 10 meters per second. However, I've also said that the initial velocity, angular velocity, was 0. So clearly if you substitute 0 here, well, this equation wouldn't work, right? So during the sliding section, this equation actually should look like this, that the velocity of the center of mass is actually less than the radius times the angular velocity, right? And this is super important. So this is in sliding area. Let's call it sliding section. All right, so what's going to happen now? Well, we can apply Newton's laws to this problem, right? We have forces, we can calculate what the acceleration is. So let's start off by defining a coordinate system here. I'm going to call everything pointing up as the y direction, everything pointing to the right in the x direction. So Newton's second law says you add up all the forces. In the x direction, that has to be equal to mass times the acceleration. And we're looking at the acceleration of the center of mass. Again, this is in the x direction. So we've only got one force here in the x direction. And since it's pointing to the left, I'm going to call that the negative direction. So it's minus the magnitude of the force of friction. The force of friction, when something is sliding, you can always write it as a coefficient of kinetic friction multiplied by the normal force. So at the end of the day, well, we have an expression here for the acceleration of the center of mass. Now it involves the normal force, and to figure out what the normal force, this is super easy, right? All you have to do now is look at the sum of the forces in the y direction. And in the y direction, I have the normal force pointing up, and I have the weight acting down. And that's it. There's no acceleration in the vertical direction, so that has to be equal to 0. So at the end, what you end up getting here is that the normal force is simply equal to the weight, and that's what we would expect. So now let's go back and substitute this guy right over here back into our expression so we can get an expression for the acceleration. So what I'm going to do here is just rewrite my forces in the x direction. So this is what it should look like. Mass times acceleration of the center of mass in the x direction has to be equal to minus the coefficient of kinetic friction, because it's sliding, and multiplied by the normal force, which we just said was mass times little g. All right, so what do we have to do? We can cancel out the masses. It doesn't matter on the mass of the bowling ball. And now the last part here is that we actually have an expression now for the acceleration of the center of mass, minus the coefficient of kinetic friction multiplied by little g. So if you were given the properties of this bowling lane sliding across, or this bowling ball sliding across this lane, we would have access to what this coefficient of kinetic friction is. I could get a number here for the acceleration of the center of mass. All right, so the first part is done. Now we have to go look at the rotation part. All right, now I want to look at the dynamics associated to the angular motion over here. And what I mean by that is I'm interested in the rotation of this and what the angular acceleration is going to look like, alpha. Now, this is related, again, to Newton's second law, but we're going to apply it to the rotational part of the problem, which says you basically have to add up all the torque acting on the system, and that there has to be equal to, again, it's not mass times acceleration in this part, it's the moment of inertia, and we're going to look at the rotation about the center. So it's the moment of inertia through the center of mass of this ball multiplied by the angular acceleration, right? This here is Newton's second law applied to rotation. Let me just write this down. Okay, so, well, we have three forces acting on the system. You have to look at all of the torque. Let's look at the torque due to the force of friction. Let's add it to the torque due to the weight, plus the torque due to the normal force. And again, that has to be equal to the moment of inertia. Well, the moment of inertia of a ball, this you can look it up in your textbook. You should find it's 2/5 the mass of the ball multiplied by the radius squared. Okay, that's the moment of inertia. If you're rotating a sphere through an axis that goes through its center, this is the moment of inertia. So I know this value. Let me go ahead and substitute this in, 2/5 mr squared. And multiplied by the angular acceleration. This is really what I'm trying to solve for in this case. So let's look at all the torque terms. Some of these are pretty simple, right? First of all, the torque due to the weight, this guy here has to be 0 because the distance to the pivot, again, is 0. And if you remember the torque equation produced by a constant force, the torque is simply F, the magnitude of the force, r, little r, I'm going to call it, is the distance to the pivot, and multiplied by sine of the angle, and that's the angle between the vector r and the vector F. In this case, the distance to the pivot for the weight is simply 0. So we don't have to worry about that one. How about the torque due to the normal force? Again, the normal force, although there's a certain distance to the pivot, actually the angle here ends up being either 0 or 180, depending on how you define it. And that one also doesn't tend to make the object rotate. Okay, the normal force does not tend to make the object rotate. So in this case, we don't have to worry about it. It doesn't produce any torque on the system. So the only thing we're left with here is the torque produced by the force of friction. And that one's pretty straightforward. So it's the magnitude of the force, which in this case is just the force of friction, multiplied by the distance to the pivot. The distance to the pivot for this problem here is simply, again, it's the radius here. Radius of that bowling ball, let's call it uppercase R, and multiplied by sine of the angle. In this case here, the angle here is 90 degrees. You don't have to worry about that. Sine of 90 gives me 1. So that's it. That is the left-hand side of the torque equation. And all of that has to be equal to 2/5 mr squared multiplied by the angular acceleration. All right, we can simplify this a little bit. Again, the force of friction, again, I know from the previous problem that the force of friction for this problem is always equal to the coefficient of kinetic friction multiplied by the mass of the ball times little g. Okay, so if you go ahead and substitute that in here, let's go ahead and do a little bit more algebra here. So we get coefficient of kinetic friction multiplied by the mass multiplied by little g. We still had a radius over here. This equals to 2/5 mr squared multiplied by the angular acceleration. All right, we're just about done now. Let's just cancel out some of the terms. We have the mass of the bowling ball, which gets canceled out. We have one radius over here, which means I can cancel out one of those. And now I'm left at the end with an expression for the angular acceleration of this bowling ball. So if I bring this over here, I have to flip the fraction over, so I'm going to get 5/2. I still have the coefficient of kinetic friction multiplied by little g, and there's also one radius that's left over here, so I have to divide through by the radius of that bowling ball. All right, this is our equation now for the angular acceleration. All right, let's put everything together now and go back to our problem and see how we can actually analyze this motion now. All right, so now here are the two equations that we obtain. We had our linear acceleration. This is the acceleration of the center of mass. And we also obtain our angular acceleration like this. Now, all of this problem is reduced to a kinematics problem because we have constant linear acceleration and we have constant angular acceleration. Now, this means, again, that I can simply write down an expression. What if I'm looking for the speed or the velocity? In this case, we know the ball's moving in the positive x direction, but this means that the velocity of the center of mass at any time is simply going to be equal to the initial velocity that I give it plus the acceleration multiplied by the time, right? This is a simple kinematic equation. Now, if you apply it to this problem, the acceleration here is this value over here. It's negative the coefficient of kinetic friction multiplied by little g. So let me go ahead and rewrite this and just put in that term. So it would be minus coefficient of kinetic friction multiplied by little g. I'm going to call this my equation 1. Now notice that the negative sign here simply tells me that the center of mass here is actually slowing down. Right? We have an initial velocity and then, again, I can't forget the time here, but as time gets bigger, notice this second term is going to get bigger, right? Which means that the velocity is going to slow down. All right, let's have a look at now the angular acceleration. Again, it's completely analogous to what we do over here for the linear term, except now we write down an expression for the angular velocity. The angular velocity is always equal to an initial plus an angular acceleration multiplied by the time. And in this case, my alpha, the angular acceleration, is given by this expression over here. So let's go ahead and just substitute that in rather than having this general expression. Now note the positive side. The positive sign is indicating that it's increasing, right? Actually, the initial value, this omega 0, is 0 for this problem, so we don't have to worry about that. But let me just finish writing this down. Can't forget the time, and divided by the radius of that bowling ball. So for this specific problem, actually, I said I didn't initially have any angular acceleration, so don't worry about that term. And now you can see what the friction does, right? The friction is actually going to, as time gets bigger, this guy is getting bigger, right? I'm getting more angular spin on that ball. All right, so we have two equations, equation 1 and equation 2. Now we simply have to combine them in order to study the kinematics now in this sliding section. Both of these equations apply in the sliding section, right? And that's really important. So what we can do now is we can find how long is this sliding section and how much time does it spend sliding, for example. All right, so let's go on the next page and do all of this work. All right, the first question we're going to ask ourselves is, when does it actually start the roll? For example, when does it actually get to this point over here? Once it gets to this point, it's done sliding, and it's actually going to begin to roll. Now, the key to this problem is that once it starts to roll, this is when I can then apply my equation that the velocity of the center of mass is equal to the radius multiplied by the angular velocity, right? When it starts to roll, this equation applies. Before that, it doesn't apply. So actually, if we set the velocity of the center of mass, is what equation 1 tells us, right? If we set this equation here, v0 minus mu k, g times t, if that equals to r times omega, which is r times this equation 2 basically, r multiplied by omega, this is the point where it's going to start to roll. So let's go ahead and do that. Now for this problem, I'm going to assume that my initial velocity is 5 meters per second and that the coefficient of friction here is 0.08. So it's a small value, just a little bit of friction between the ball and the lanes. Okay, so we got to do a little bit of algebra here. What we can do first of all is just simplify this. And now we have to group the terms. Notice I have time here on the left-hand side, and I also have time here. So let's group all those terms together. My goal at the end is to solve for the time. So let's bring this over to this side. This is, it has the same terms, right? Mu k multiplied by little g, but you notice that the fraction here is different. This is 5/2, and this is going to be 2 over 2, basically. So this is what it looks like. So we get v0, which is going to be equal. When I bring this on the other side, it becomes 7 over 2. And again, it's still the coefficient of kinetic friction and multiplied by this. So the last thing I have to do is simply isolate for time. So let's go ahead and do that. So the time at the end of the day should be like this, 2 over 7 multiplied by v0 and divided by this coefficient of kinetic friction multiplied by little g. All right, this is the expression I have when it starts to roll, right, at this specific time. So let's go ahead and substitute our values, see if it makes sense. So 2 over 7, v0 was 5 meters per second. We can put 5 up here. Coefficient of kinetic friction was 0.08, and little g will just take 9.8. Put that in your calculator. I think I did things correctly. I think we get 1.8 seconds. So after 1.8 seconds, the ball will begin to roll. So from time equals to 0 all the way to time equals to 1.8, it's actually sliding. All right, the next part is, how far is this distance s here? All right, we know it takes 1.8 seconds to start the roll. However, how far is this distance? Again, this is simply a kinematics problem. What you're looking for is the distance delta x, which in this problem here, I'm just calling the distance s. Now, there are two terms. There's an initial velocity term. So our kinematic equation should look like this. And there's also an acceleration term, right? So we have two terms to our kinematic expression. Now what I'm going to do again, this acceleration I know from the previous problem. This acceleration was mu k multiplied by little g, and we had a negative sign because it was actually slowing down. So let's go ahead and substitute in all our values here. And the time we know is this, it's 2/7. You can either substitute 1.8 seconds if you want. It really doesn't matter. I'm going to just keep all the variables in there for now because I just want you to see how everything kind of breaks down at the end. So we get v0, here we get mu k multiplied by little g. That's our first term. And then we get minus 1/2. My acceleration, the magnitude was mu k by little g. I've just taken the negative sign and put it here in the front. And the time, again, this looks a little bit messy, but it's not that bad. 2 over 7. v0 mu k multiplied by little g, and don't forget to square this second term. All right, now you have to do a little bit of math, okay, in order to kind of simplify this. And at the end, the distance s that you're going to get should look something like this. I get 12 over 49, right? The 49 comes from squaring this 7 over here. And the 12, well, just figure that out for yourself. I think you could do this part. And the rest of the terms are going to look like this. v0 squared and divided by coefficient of kinetic friction multiplied by little g. Now you substitute in all the numbers, so you get 12 over 49. I'm going to get 5 squared. And this term here is the same as before, 0.08 multiplied by 9.8. That's our little g value. So I calculated everything, and at the end, what I ended up getting was that the value S, I got approximately 7.8 meters. So that would be that distance where it's sliding. So this region over here, right, the distance from here to here, that 1.8 seconds. In 1.8 seconds, that bowling ball has gone approximately 7.8 meters. That seems kind of pretty realistic, actually. If you consider a real bowling lane, let's just kind of make sure that our result makes sense physically, right? A bowling lane is approximately kind of 60 feet, right? 60 feet is, say, roughly 18 meters, right? So you're about, not quite halfway to 18 meters, and that seems quite reasonable over here. The other thing you can ask yourself is how fast, right? Once it gets over here, how fast is it moving? How fast is ball moving? When it starts to roll, and this again, you simply use our kinematic equation. You can use my equation over here. You know the time. You know our time is 1.8 seconds. We know the initial velocity was 5. Therefore, you should get something smaller than 5. So at this point over here, once it starts to roll, I found a velocity of the center of mass, which was approximately 3.6 seconds. Okay, so there's the bowling ball problem, folks. Hopefully you understand all the steps. And the key point is to relate the angular velocity to the linear velocity. And you can only use my equation over here when it starts to roll. And in the section before that, you can't write this expression down. It doesn't make sense. All right, have a great day, folks.